Now, sadly, I do not have the book. Um, so I'm going to look up the mass of a bacterium. So I'm going to look that up in Google. Mass of a bacterium. And let's see. E. coli has a mass of 1 picogram, which is 1 times 10 to the negative 12th grams. Now, the mass of a proton is, and I'm going to look that up because I don't know that by heart, 1.67, whoops, come on, times 10 to the negative 27th power kilograms. Now, this is for bacteria. Okay, this many grams, let me erase this. There are 1,000 grams in a kilogram. I remember that by deca, hecto, kilo, 10, 100,000. So I need to take 3 off of this. Okay, so now if I take the mass of bacteria, which is 10 to the negative 15th power, and whoops, I divide it by 1.67 times 10 to the negative 27th power. But then I also have to divide it by 2 because there's just as many protons as neutrons. I would get 3 times 10 to the negative, times 10 to the 11th power. So I'm getting 10 to the 11th power. Oh, but it says protons or neutrons. So now I'm going to take that 2 away, and that's going to give me 6 times 10 to the 11th power, which is really 10 to the 12th power. We round it to 1 significant digit. That's our answer for A. B, DNA molecule. Well, let me look up the mass of a DNA molecule. Okay. It's saying 650 grams per mole. So let's go with that. DNA is 650 grams, or let's write it in kilograms, 0.650 kilograms per mole. And 1 mole is 6.022 times 10 to the 23rd particles. Okay, so that would give us how many kilograms? And then we just have to divide by the mass of a proton. So 27. Okay, let's put that into a calculator. So, whoops. Get out there. Okay, so we've got 0.65 divided by 6.022 times 10 to the 23rd power, 1.67 times 10 to the negative 27th power. That gives me 646, which definitely does not make sense. So I need to figure out what I did wrong. Okay, so this 0.650 kilograms per mole, that just wasn't right when I looked it up on Google. So let's try this again. I need to read more closely. It says here that it's the number of base pairs times that 650. And then I see somewhere else that the molecular weight of E. coli DNA is 3.5 times 10 to the ninth power, or 3.1. So let's write that down. 3.1 times 10 to the ninth power, but that's in grams. I want it to be in kilograms, so I need to subtract 3 off of that. So I'm going to change that 9 to a 6 and then write it as kilograms. Let's try that. 3.1 times 10 to the sixth power. I need to go to Desmos. So I need to replace this with 3.1 times 10 to the sixth power, and that gives me 10 to the ninth power protons or neutrons. And that seems more reasonable. Okay, C. Let's see if we can start with a better weight here. Human body. Well, the human body, probably on average, it's probably around 160 pounds. Okay, so I think there's 2.2046 kilograms in a pound. I better double check that. I can't type. I know this for sure. Yeah. So there's 2.2046 kilograms in a pound. And now I just have to divide that by the 1.67 times 10 to the negative 27th power. And that'll give me the answer. Okay, so where is it? Here we go. 160 pounds, 2.2046. So that'd be kilograms. Divide by 1.67 times 10 to the negative 27th power. So that would be 10 to the 29th power. Protons and neutrons. And now our galaxy. Oh my goodness. Mass of the galaxy. Milky Way galaxy. D. Okay. So it says here 1.5 trillion. So what is this? This is 1,000, million, billion, trillion. Okay, 1,000, million, billion, trillion. That's how many solar masses. But what's the mass of the sun? Times 1.989 times 10 to the 30th power. And then we just have to divide that by the 1.67 times 10 to the negative 27th power. Okay, so let's do this. 1,500,000,000,000,000 times 1.989 times 10 to the 30th power. Take that whole thing and divide by 1.67 times 10 to the negative 27th power. That gives me 10 to the 69th power. Protons are neutrons.